Today's video is titled Fun with Spacecraft, or It Does What? By me. And there's my disclaimer. I am smarter today than I was yesterday. It's only because I read the paper. But trust me, not near smart enough to write this thing. So let's get right into it. Lots of talk about SDO and this crazy idea that is the sun going dark? What I hope to do, along with my colleagues, Steve Olson, Chris Potter, Jeff P., Richie from Boston, all these great guys and ladies. What I hope to do is working with these great observers is to produce videos that when we're seeing observations that we can come back and at least apply theoretical physics to it. Do the math. Now, I really don't care what others have to say. You can criticize all you want, but before you make the criticism, produce your own paper. And let's see what your math comes up with, and then we'd have something to have an intelligent conversation with. Otherwise, you're nothing more than a troll, and we don't need you. If you're here to learn, then how about what I tell people, the best investment you could make is to go out and buy some Gorilla Tape, because it's stronger than duct tape, and then pull a piece of it off, measure it. I'd probably go for about a good 6-inch piece, and then put it over your mouth. That way, you got one mouth, you got two ears. The whole idea, the way that the body was designed, was that use both what you got more of and less of what you have one of. You'll go through life a lot more happier. So, as Professor C is showing here, this is theoretic. It's a theory on applying what observation is. And please point out what the professor shows here. I love this. In physics, observation is king, and theory a servant of it. Folks, can't be any more plainer than that. So we're talking about, all right, if we have this hypothesis that the sun is somehow or another changing for the worse, well, we want to go and look at this and say, okay, let's figure out where the SDO orbit is at. And that's what we do here. So in this document, the professor is going to use the numbers that he was given to do some calculations and demonstrate what they reveal about the SDO orbit. In all of the channels I see out there and of all the videos and the pictures, I don't see anyone doing the math. And I think that this is what makes us different. So let's continue. So we're using the information that has been given on SDO's orbit. Now, here is the calculations. So T stands for 23.93 hours. The orbital attitude is H equals 35,785.68 kilometers. That's the geosynchronous orbit. Orbital inclination is at 28 degrees. Position at a minus 105.78 degrees longitude at 13.38 local time, which equals 20.38 universal time. Other known constants that will be used. The Earth's orbit is represented by T, which equals 365. R is represented by 6,371 kilometers. Sun's radius, as you can see, make sure you follow this, folks, now, because this is going to be important. The Earth's sun, which is represented by D, equals 152 million kilometers, which is 1.5 to 10 to the 8th power kilometers. Percentage of Earth's radius, 1%. Now, from these values, we can begin to do some basic calculations. As you can see, the professor has taken the time to write the math out. What are we looking for? We're looking to understand the orbit of the Solar Dynamic Observatory satellite. That when we begin to see the anomalies that we have been recording, we're not buying the flying cheese sandwich any longer. We're calling you, NASA, and I'm calling anyone else out there. You want to put the math and argue this, then bring it on, buddy. You know? Hey, remember the Matrix? I am saying bring it on. But let's continue. I digress. So, we're beginning to understand how this satellite is to the Earth's orbit. You getting it? Okay, let's move on. Figure 1, the SDO's orbit and the Earth to scale. There we go. Figure 2 shows SDO at different times during Earth's orbit around the Sun. When the Earth is at position A and B, the SDO satellite will be behind the Earth for a period of time each day. Okay, we get that. We know. All right, let's continue. Figure 2. SDO's relative position relative to the Earth's position at 4 times during Earth's orbit around the Sun. At positions A and B, SDO should go behind the Earth for a period of time each day. To find the maximum time during which the Earth will cause an eclipse, we considered half of SDO's orbit, the part behind the Earth. SDO is in that part of its orbit during half of its period, or 11.95 hours. It goes through 180 degrees of its orbit in that time. So the maximum time that it can be behind the Earth and not be able to see the Sun is, and there's the math, which works out to approximately 1 hour, roughly 15 minutes. So the maximum time the Earth can create an eclipse as far as SDO is concerned is 1.15 hours or 69 minutes. If we want the total time during which the Sun is completely dark from SDO's point of view, we need to subtract the time during which SDO is able to still see the Sun through the Earth's atmosphere. Now, the atmosphere is 1% of the Earth's radius. So SDO may still be able to see part of the Sun for another 0.02 seconds of 69 minutes, which is, excuse me, I said that wrong, is 0.02 of 69 minutes, which is 1 minute and 38 seconds. But it may not be able to see through the whole atmosphere. So let's stay with the maximum time period of total eclipse of 69 minutes. Now, the cycle of eclipse would repeat itself every half of a year. So the eclipse cycle period would be, and there's the formula. Okay? So every 182.5 days, the eclipse cycle should repeat itself. If we use the more accurate orbital period for the Earth of 365.25 days, then the cycle should repeat itself every 182.6 days. Next, we will estimate at what time of day we can expect the eclipse to happen. And also, when do we expect it to happen in subsequent and previous cycles? Now, we know that SDO was over a point on the Earth where the time was 1338 local time, and that time was 20.38 universal time. The time of delay of 13.38 is 1 hour and 38 minutes, or 98 minutes, from the midday position when SDO would be exactly between the Earth and the Sun. So we can expect the midpoint in the eclipse period to be 12 hours minus 98 minutes, i.e. in universal time, the midpoint for the eclipse time period should be, and here you go, at 7 o'clock. Now, the maximum eclipse period is 69 minutes. So the eclipse should start and end about 34 minutes on either side of the midpoint at 700 universal time. This means that it should start around 6:26 universal time and end at 7:34 UTC. Now, we will look at the observations to see if they are what we would expect from this theoretical exercise. Tables 1 show the times during which the sun went dark in 19.3 nanometers of the ultraviolet light spectrum in August and September of 2016, this year. The data points so far observed are from August 20th to September 7th. From the table, we see that the time during which the sun disappeared for the longest period of time was September 2nd, when it was gone for 70 minutes. But the longest time for which the sun was partially gone was actually August 30th. Times could not be determined for August 31st, and the time when the sun is completely back on September 1st was uncertain. So it is hard to determine the exact midpoint for this cycle. However, there is no uncertainty with the times on September 2nd, and the time during which the sun was completely gone on that day was 70 minutes. This is 1 minute more than the expected maximum, but we can here put it down to uncertainty in measurements. Only hours and minutes are used, not seconds. The time period during which the eclipse is supposed to happen is between 6:26 and 7:34, which agrees with the times in Table 1 up to August 29th. The dark sun phenomenon started earlier than that after the 29th, started at 6:17 on September 7th, showing the midpoint for that cycle cannot be 700. This is discrepancy number 1. Got a problem here, folks. Let's look at this detailed. Now, you can begin to see here for yourself. NASA, Jet Propulsion Laboratory, Naval Observatory. Y'all want to have a cup of coffee and crunch some numbers? Because something's going wrong here, folks. Now, I'm not going to take the time to go through each one of these. Take a screenshot. Look at this, folks. We're coming at this from an approach that says, okay, we hear what the powers to be are saying, but our observations are showing something else. Thus, we have discrepancies. Here's our first. Time's not working out. Table 2 shows the times during which the sun went dark during the February-March cycle. The number of days between the beginning of the February-March cycle and the August-September cycle is 184 days. The expected value from the Earth's orbital period is 182.5 days. This means that there is a discrepancy of 1.5 days. Okay. Also, since the period for the eclipse cycle should be 102.5 days, we would expect that if the eclipse is happening between, say, 6:26 and 7:34 in one cycle, then it should be happening 12 hours later in the next cycle, i.e. 1826 to 1934. But the sun is going dark between 6:33 and 7:43 during the February-March cycle at the midpoint of the cycle on March 2nd, which is a similar time of day as during the August-September cycle. This is a very large discrepancy that cannot at all be attributed to an experimental error. Discrepancy number 3. Table 3 shows the times during which the sun went dark during different days falling within the expected cycle from September 2015 to September 2010. Notice that the times are similar for the February-March cycle and the August-September cycle. And all the times during which the sun goes completely dark fall between 6:14 and 7:39. None are 12 hours later, as we would expect from the Earth's orbital period. This is discrepancy number 4, and it tied to discrepancy number 3. Notice as well from Table 3 that the data point of March 11th or September 11th, which was proposally chosen for the conduction of a search over different years, which was chosen because it was well into the sun going dark cycle for the February-March 2016. By September 11, 2011, it became obvious that the day was now too close to the beginning of the cycle, so a search was also done on September 13th, and then the search during the next cycle was shifted even more to September 15th, 2010. This is an indication that the cycle is indeed longer than 6 months, agreeing with the period arrived at from comparing the cycle in August-September 2016 with the cycle in February-March. This augments discrepancy number 2. Got a problem here, folks. Remember Mr. Schwartz, you probably don't remember my algebra teacher, but that's what he was. That was his name. And he was one of those guys who really did believe that math could save your life. Who knew? All right. So we're starting to see, and you know, folks, this is where we try to apply the science and the math to what we're seeing, because it's not adding up. So, as you can see, the tables are very well done. All right, let's go on. Discrepancy number 5 comes from the fact that the SDO was launched on February 11, 2010. So following this cycle, we should have had eclipses happening about every 3 weeks from February 20th or later of 2010. The images are available, but there is no sign of the sun going dark during that period. What? Did you catch that? Table 3, time intervals during which the sun turned dark and the 19.3 nanometers ultraviolet light was also detected by SDO satellite in the years 2015 to 2010. The last column indicates whether the sun went dark in the visible light. Let's look at this. Yes, 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 no. No, yes, yes, no, no. What? What's going on here? Well, here we go. Folks, we really have what I think is a mystery here. All right, let's go on. Figure 1 shows the sun going partially dark on September 15, 2010. So here we go. We're probably talking about this period right here, it looks like. Yeah. The images shown are 1 minute apart from 6:41 to 7:08. The sun starts going dark after 6:42, but never goes completely dark. Notice that there is a decrease in brightness between 6:40 and 6:41. And I've been noticing this as well. The sun is not as bright as it has been. You could say, well, maybe the camera's gone bad. But boy, you know what? It's like the Secchi thing. So let's see. We got one camp that says lens flares, lens flares. We got the other camp saying, no, it's the camera. I've concluded that NASA, what are you sending up in space? A bunch of junk? Come on. Guys, that's no camera anomaly and it's no lens flares. Get your head into the sunshine. It'll do you good. Admit it. You don't know what it is. Neither do we. Let's go on. So, we just see a tiny bit of the corona gone from the bottom left in the 641 image to indicate that the sun is starting to go dark. Now, the darkening effect on the sun between 640 and 641 cannot possibly be attributed to the fact that SDO is now looking through some of Earth's atmosphere, because only a third of the sun, 33%, see 0.5 on pages 1 and 2, can coincide with SDO looking at the sun through Earth's atmosphere. And this effect is seen over the whole surface of the sun. Now, folks, I don't care what you're saying. Again, NASA, you ain't... Listen, your name in Hebrew means deceiver. You certainly are living up to that, aren't you? The last two images also show that there is a marked increase in brightness between 707 and 708. The sun was already completely visible at 707. So there is no way of attributing this marked increase in brightness to an eclipse. It has to be that the sun's ability to emit light was affected, and its normal ability came back 1 minute after the whole sun was again visible. Figure 2 shows the images of the sun detected by SDO between 640 and 707. The sun also never quite goes completely dark, as in the 13.1 nanometer images. The first two images in Figure 2 show that the sun at 640 was perceptibly brighter than at 641. This effect is similar to what was seen with the 13.1 nanometer images and cannot, as stated before, be attributed to SDO looking at the sun through Earth's atmosphere, as the whole surface of the sun is affected. The only possible explanation is that the sun's ability to emit light was reduced before the darkening of the surface began. People, we got a problem. We have the evidence. We're getting the science. Figure 2, images of the sun is detected by SDO in the 33.5 nanometer ultraviolet range between 640 and 707 on September 15, 2010. Figure 3 shows images in the 33.5 nanometer wavelength. Okay. The image from 707 is the last image shown in Figure 2, when the whole surface of the sun was again visible after being dark for a period of time. Notice how much brighter the image at 708 is than the image at 707. Talking here. Oh, excuse me, I'm wrong. It's between these two. And there is, look at that. Wow. Okay. And if you're getting seasick, sorry about that. Figure 3 shows the images again. Notice how much brighter 708 is than 707. There is a marked increase in brightness, which, again, can only be attributed to the fact that the sun's ability to emit light was affected, and not at all due to an eclipse. The images in Figure 3 also show that the corona grows in both sides of the sun between the time 707 and 708, or in the time span of 1 minute. This is another piece of evidence that shows that the sun going dark has nothing to do with an eclipse and everything to do with the sun's ability to produce light, which is being affected. Image 3, Figure 3, images of the sun as detected by SDO with the 35.5 nanometer ultraviolet light spectrum at 707 and 708 on September 15, 2010. There is a marked increase in the sun's brightness between the two images. Now we actually went in and put into the timetables which the sun turned dark in various ultraviolet wavelengths as detected by the SDO satellite on September 15th and 16th, 2010. Table 4 shows the times during which the sun was affected by the darkening cycle on September 15th and September 16th, 2010 at 3 different wavelengths. On September 15, the sun did not completely go dark in all wavelengths shown, but the times when it was first affected are slightly different, with the sun losing some of the 30.4 nanometer emissions at 640. Whilst it's only first lost some at the 33.5 nanometer emissions at 641. The time when the 13.1 nanometer emission was first affected was even later at 642. Also, the sun's emission was affected for different times, as the last column in Table 4 shows. Right here. Notice that the reduction in the 30.4 ultraviolet wavelength emission started before the reduction in the other 2 wavelengths was apparent, and yet was the one that lasted the longest, 28 minutes. This cannot even be explained with an argument that the discrepancy is due to slightly different images updating times. Because if this was the case, the wavelength that was affected first would be the one to also reappear first. Okay, so we got a problem here. The fact is, the evidence is showing that the sun is losing its ability to emit light. Now, this has been a long video. First one I've ever done that was 30 minutes. And the last part of this paper gets into why the evidence is showing, folks, something's up with the sun. I'll finish up. The difference in starting times and the times during which the sun's ability to emit light was affected is even more marked on September 16th, 2010. Also, the sun went completely dark on that day, which didn't happen on the previous day. The starting times for these 3 wavelengths vary between 625 and 639, and the time periods during which the sun is at least partially darkened varies between 37 and 52 minutes. This is a difference of 15 minutes and cannot at all be explained by an eclipse. This would require the SDO satellite to be in a different place at the same time. No, this is consistent with the fact that the sun's ability to emit light is being affected. Figure 4 shows the images of the sun in September 16, 2010, the 17.1 nanometer between 717 and 732. There is a slower but marked increase in the sun's brightness over this period of time. When the whole surface of the sun first appears at 717, it's at 17.1 nanometer, and the ultraviolet light emission is a lot weaker than it was at 732. However, there is now a more gradual increase in the sun's brightness than on the previous day, where the sun's brightness increased from 1 minute to the next. This shows that the sun's ability to restart its emissions was reduced from what it was the previous day on September 15, 2010. In conclusion, I think it's obvious that the idea that the sun becoming dark because of an eclipse or by the Earth being in the way of SDO's cameras is inconsistent with the observations that SDO itself has provided. The sun is going dark for a period of 24 days every 184 days, and it is also weakening. This can only be attributed to its energy being drained by some mechanism or cyclic basis with long-lasting and progressive effects. This suggests that another star is draining our star of its energy. Well, folks, there you go. You probably could capture all this. We're going to get this where we get permission. You can get the screenshots. This is the paper, 9 pages. I challenge anyone who would like to dispute the theory or the fact. Something's wrong with our star. If you have a paper, if you have different calculations, let us see them. Let us talk. This is good science. All right, my friends, be kind to one another.